Thermodynamics dictates a specific trajectory for the physical world. Order naturally decays into chaos. Drop a glass, and it shatters into thousands of random fragments. Energy dissipates, and systems move toward a state of disordered equilibrium. Yet the universe we observe is filled with the opposite. We see the highly organized geometry of spiral galaxies, the stable orbits of planets, and the dense complexity of biological life holding its shape over billions of years. This creates a contradiction. If the physical laws of nature pull toward chaotic dispersion, there must be a mechanism at work that is actively stabilizing matter and preventing it from dissolving. While we can measure the pull of gravity or the strength of an atomic bond, traditional physics describes how these forces act, but not the underlying reason why the universe continues to select for complexity over heat death. This has led researchers to look past physical matter and examine the information that defines it. A new proposal called the second law of infodynamics suggests that information systems operate under a different set of constraints. Unlike physical systems, information seeks to minimize its own entropy over time, evolving toward states of higher symmetry and lower data complexity. This infodynamic rule works as a balancing mechanism against physical decay. It drives the universe to organize and compress its data, seeking the most efficient possible configuration for any given system. To understand how this hidden layer of data creates the appearance of a solid world, we have to look at how the universe organizes itself at two different scales: the microscopic synchronization of fields and the macroscopic compression of cosmic structures. The quantum universe isn't solid points. It's a continuous, chaotic field of vibrating information. When these random fluctuations synchronize, they achieve phase coherence, locking into a rhythmic grid. As this coherence increases, the field stabilizes into a self-sustaining geometric structure called a reality knot. These localized knots are exactly what we perceive, measure, and interact with as solid atomic matter. This means a solid object is not a static thing, but a specific region of the field where information is actively cooperating to resist the natural pull toward disorder. If matter is just stabilized information, why do these individual knots pull together across millions of miles to form stars and planets? Consider the computational burden of cosmic dust. Tracking millions of scattered particles across a vast void requires immense processing power and creates high information entropy. The universe solves this by collapsing the dust into a single planet, reducing variables and dramatically lowering information entropy. This drive to minimize data complexity and save processing power is the actual origin of the force we identify as gravity. Gravity is effectively an optimization algorithm, a cosmic data compression system that keeps the universe running with the least amount of informational effort. When we combine these two scales, a new picture of reality emerges. Matter is information stabilized by microscopic coherence, and gravity is data compressed by macroscopic optimization. Because the universe uses these specific data-saving mechanisms, many physicists now hypothesize that reality operates as a computational process. If the universe functions through bit-state minimization, then the laws of physics can be viewed as the governing code, the mathematical parameters required to keep the system stable and computable, and explains why order persists despite the second law of thermodynamics. While physical energy tends to disperse, the informational structure is programmed to build complexity to ensure its own efficiency. Everything in existence, from the device you are holding to the atoms in your body, is a continuous, active computation, fighting off the void to keep reality rendered.